Okay, we can start with the review part. So last time we learned about pure substance versus mixture, and we learned that matter can be separated into pure substances or mixtures. Pure substances are only one type of substance. They cannot be separated by physical methods. But for mixtures, two or more substances can be mixed together to form a mixture, and they can be separated easily using different methods such as filtration, distillation, and more. And for pure substances, this can be categorized into two separate categories of elements and compounds. Elements are only one type of atom, and compounds are more than two types of atoms. Mixtures, there are homogeneous mixtures, which means that they are evenly mixed. And there are also heterogeneous mixtures, which are not evenly mixed. Can everyone hear me? It's cutting out a little bit. Okay, sounds good. Yeah, this is another slide of pure substances and mixtures. You can see that pure elements only this it's only made out of this blue spheres, which signify one element, one type of atom, and there for compounds you can see multiple atoms joined together, but they are the same elements. They're evenly um all of them are the same type of element. And for mixtures, you can see that there are different types of elements. You can see this green substance existing together. You can see these green balls, and you can see this another molecule which has two red balls and one blue ball. You can see that these are different substances and they're mixed together. And although it's not really shown here, you can see that the proportions, let's say there are five of these green atoms, and these different types of um, substances, there are almost exactly the same amount. So you can see that they are evenly distributed. And examples are salt water. If you dissolve salt in water, it seems like it disappears, but it is evenly distributed in the water, and it is still a mixture. Air is another type of mixture, although you cannot see each component that makes up the air. It is because it is evenly distributed, you cannot see much of a difference. And there are also heterogeneous mixtures you can see on the right. And you can see that there are multiple substances that cannot be mixed together. I think an example here which shows the picture, is oil and water. You can see these bottom, they're lipids, oils, and you can see water molecules around here. And you know that water and oil cannot mix together well. They cannot be evenly distributed. That is why they are heterogeneous mixtures. Some other examples include, you can think of pizzas. You can see a lot of toppings, but they're not really mixed together evenly. Same with salads and, for example, landfill, which contains a lot of different types of substances in the soil. So a substance which is made up of the same kind of atoms is called an element. For example, water, table salt, ammonia are, do you guys know what kind of element this is? These are water, table salt, and ammonia. We can quickly go back. You can see here that water, H2O, table salt, NaCl, ammonia, NH3, are composed of more than one atoms. Therefore, they are compounds. Talked about how more than one atoms of the same element are called compounds. Then what type of element are copper, oxygen, and diamond, which is also copper, which is also carbon. You can see over here, for pure substances, if it's made up of only one type of atom, you can see it's an element, it's a pure element. You can see that all of copper, oxygen, and diamond, which is carbon, are made up of one type of atom. Therefore, they are elements, they're pure elements. Salt water, air, tea are, do you know what these matters are? They are definitely a mixture. You can see salt and water is a mixture. Air is a mixture. Tea is a mixture. But do you guys know what kind of mixture this is? Quickly go back to. Is it a homogeneous mixture or a heterogeneous mixture? For salt water, air, or tea? Yeah, they are homogeneous mixtures because they are evenly distributed. They are mixed together very well that many of the substances within the mixture, cannot be really seen because they are mixed together very well. Sand and water, or oil and water, are examples of heterogeneous mixtures. It's the opposite of homogeneous mixture because sand and water do not mix together well. They cannot be evenly distributed. And oil and water, like we've talked about before, cannot be mixed together well as well. A mixture of alcohol and water can be best separated by, now we are getting into separation methods for mixtures. If you notice, alcohol and water have different boiling points, and they are both liquids. What we can do is we can separate them by distillation, We will talk about that we'll review that in the next slide, but let's do this last question really quick. What is usually used for separating liquid and solid? Do you guys know? Yes, I heard filtration. That is correct. Filtration used for separating liquid and solid. Again, distillation is separating liquid and liquid. Do you guys have any other question so far about elements or mixtures? If there are no questions, I can move on to the next slide here. This shows few types of filtration. On the left, you can see a beaker containing a mixture of a liquid and a solid. And if you pour this mixture into this funnel, you can see that it has a filter paper. These filter papers are made up of multiple pores, multiple holes. It only allows for the liquid to pass through the filter paper. And you can see that all the solid is gathered up on top because of this filter paper. And these solids that are left on the filter paper are called the residue. And whatever liquid goes down the funnel into this second flask, it's called the conical flask, are called the filtrates. The liquid that has been filtrated by the filter paper, called a filtrate, and the solid that remains on the filter paper are called the residue. On the right, here is another example of a different type of filtration method, and this is usually for liquids that settle at different layers. So you can see these different layers of green liquid and a yellow liquid. This is really useful when you're separating, for example, oil and water. If you mix oil and water and leave it out for a little bit, they will settle out to have two different layers, one for the water and one for the oil. What you can do is pour it into this separating funnel, which is shaped like this. And here is a tap in the middle where it is attached to. And what you can do is slowly turn this tap and only allow this denser liquid to go down and collect in a separate beaker. And you can see there is a stand over here. A stand holds up the separating funnel. Its job is to hold up the separating funnel. And again, the tap is used to turn the knob and control the flow of the liquid. If you twist it more water will go down more quickly. And you can close the system by turning back. And you would use it to separate two layers of liquids. And this is the distillation method that I have talked about before. Simply reviewing, there is this burner here, which is under this mixture of different substances. For example, you can have a mixture of liquid and liquid, and this is really useful to use distillation because it uses different boiling points. So, for example, if we have water and alcohol in this mixture, alcohol has a lower boiling point. So if you heat it up to the alcohol boiling point, but not quite the water boiling point, only the alcohol will evaporate. And it will go down this condenser and then goes back into this liquid form and collect at the receiving flask. And the water will remain here, still at the distilling flask. And you will finally have two liquids separated from the mixture. That is the distillation method. Now we're moving on to this last part of chemistry lesson, which includes water cycle, including condensation and evaporation, and measuring volume and mass, how to calculate density, chemical change and physical change, osmosis and diffusion, semi-metal, metal and non-metal, and SI units, your standard units. Okay, so this question. Steam changes to liquid by a process called steam is a gas and it changes into a liquid. So does anyone know what this process is called? This process is B, condensation. And let's look at the different changes of states of matter that has different properties. So let's talk about condensation first, which was the answer to the question. So condensation happens when warm vapor cools down and it turns into liquid. So again, condensation is when a gas turns back into a liquid, and this is due to cooling. This happens when the gas loses heat and forms tiny droplets. Doesn't have to be water. Examples include dew formation. For example, water droplets can appear on grass in the morning due to the cooling of the air. Another example is a foggy window. For example, car windows fog up when warm breath meets cold glass. And water droplets on a cold drink. Another one, if you have a cold drink or a bottle of water, there is sometimes those little sweats, which kind of form when the cooling of the liquid touches the gas. So the gas condenses due to cooling of the drink. And another example is cloud formation, when water vapor in the air cools and forms clouds. Another example is a mirror fogging up. For example, steam condenses on the mirror. And another process is called evaporation. And evaporation happens when a liquid slowly turns into gas due to heat. So it is the opposite of condensation. It happens at any temperature, and it is not just boiling. Um, People often mistaken is evaporation is boiling, but it can happen at any temperature and not just the boiling temperature. But it occurs at the surface of the liquid. You can see on the right, here is a liquid, and only the molecules at the surface are evaporated and are slowly turned into gas. Um, It's comparing it to boiling on the right, where molecules of even within the liquid starts to turn into gas. That is the difference. Boiling, for boiling, every part of the liquid starts to turn into gas, but for evaporation, only the molecules on the surface starts to slowly turn into gas. And again, it happens at any temperature. If it's not 0 Kelvin. An example is wet clothes drying on a warm day. When you can see when you hang the clothes on the clothesline, the warmth of the sunlight dries the wet clothes by evaporating the water on the clothes. Another example of evaporation is sweat cooling the body. So sweat evaporates from the skin, and that helps cool the body. Another example is puddles drying after rain. There is a rain, then the puddles will eventually dry out because of process of evaporation. All of these have a common example of water turning into gas, a liquid turning into gas. That is the process of evaporation. The water cycle is an example of combination of evaporation and condensation. So for example, in lakes or rivers or in the ocean, water starts to evaporate and it turns into water vapors in the air. And water vapors, once it is in the air, it condenses. So gas slowly turns into liquid. And you can see these clouds are formed by condensation. And after that, there is a process of precipitation, which basically means that water is dropped back, rained back into the earth. And once it is collected or used by other organisms, it can be cycled back into bodies of water like a lake, river, or ocean. And this process can begin again. Evaporate it, condense it, precipitate, and over, and that is the water cycle. So if we go back to this question, for 37, steam, which is gas, changing into liquid is, we can see that it is definitely condensation. Next question, a person urinates more often in the rainy season than in the dry season because um, urinating happens more when you have more water in your body. So why would that be the case for rainy season? Is it because more sweat evaporates from the skin, or B, less sweat evaporates from the skin, or C, his kidney works faster, or D, he drinks less water? I think I heard B, and B would be correct because you can see that definitely answer choice A and D are incorrect because it's saying that more sweat evaporates, and if you have more sweat evaporating, then water is moving out of our body. And also, if he drinks less water, then the person will have less water in their bodies and therefore urinate less. That would not be the right answer. It's either B or C, but B is the most reasonable answer here, since less sweat evaporates from the skin during rainy seasons. We can connect that. And less sweat evaporating means more water is retained in our body, and thus a person urinates more often. Next question. A student is to measure 20 centimeter cubed of a sodium hydroxide solution. What instrument could be used? So we are moving on to volumes, mass, and density. And a student is wondering what instrument can be used to measure the solution, to measure the volume of the solution. What can be used? Is it a measuring tape, which is used to measure lengths of usually solids? Is it a hygrometer, which measures humidity? Is it a measuring cylinder, which is used to measure liquid volumes? Or is it hydrometer, measures the density of a liquid? Well, we have a liquid solution, and since we are trying to measure the volume of a liquid, the right answer choice would be C. The measuring cylinder would be the best instrument to be used to measure the volume, because measuring cylinder, I will show in the next slide. Here is a measuring cylinder. It's also called the graduated cylinder. And this would be the best instrument to use to measure the volume of a liquid accurately, because you have these markings which you can pour the liquid inside here. These markings are in milliliters. That might be a little problem because we wanted to find measure the 20 centimeter cubed of a sodium hydroxide. But we know that milliliter can be converted to centimeter cubed by simply saying 1 milliliter equals 1 centimeter cubed, 1 cubic centimeters. So 1 liter, which equals 1,000 milliliters, which equals 1,000 cubic centimeters. Oftentimes, beakers are a little less precise because it is used to measure large volumes, and sometimes there can be some off numbers. It may not be exact, but graduated cylinders or syringes or burettes or pipettes or volumetric flasks only only the pipette, burette, syringe, graduated cylinder are used to measure precise volumes because it is only measuring small amounts of liquid. You can see that only small amount of liquids can be entered through maybe the top, and it makes less errors. But beakers and volumetric flasks, however, can hold up to large volumes and may not really be exact. And volume is the amount of space an object occupies. So we can measure a volume of a solid by using maybe a measuring tape. We can see that the length of this object is 10 centimeters. The width of this object is 6 centimeters, and the height of this object is 5 centimeters. For this cuboid, which is what this is called, what this shape is called, can be found by multiplying the width, the length, and the height. So 10 times 6 times 5, you can find it to be 300 cubic centimeters. A single length is just a centimeter. If you have an area of one side, then it is centimeters squared. So if you're multiplying 5 centimeter by 10 centimeter. But if you're finding the volume, then it becomes the cubic centimeter. You can measure the liquid volume like we've talked about before by using a beaker or a graduated cylinder for more precise purposes. If you use that, you can see the marking to be 80, and this marks 80 milliliters. But this can be converted to 80 cubic centimeters, since 1 milliliter is equal to 1 cubic centimeters. And how you would look at the graduated cylinder is by looking at this meniscus, it's called here. It is a sort of upward or downward curve at the surface of the liquid. So when you have lined up the solution in the graduated cylinder, you'll look from the side of it, and if once you look at the side, you can see that it touches around the 20 milliliter mark. What you do with the meniscus is you try to find the lowest point of the meniscus. And you can see the lowest point touches the 20 milliliter mark. So you can mark this liquid as having the volume of this liquid volume is equal to 20 milliliters or 20 cubic centimeters. The next question, which of the following instruments can be used to measure the diameter of a circle? A diameter of a circle is basically just the length from one end to another. This is the diameter. Just passing through the center and just connecting any two ends. How would you measure this length right here? Is it a meter ruler, or a thermometer, or an ammeter, or a string? Yes, that's right. The answer is A. Is it correct? Since meter rulers are used for measuring straight line distance across center. And that is the diameter. So a meter ruler is really good for using to measure the diameter, since it is again straight. These are different instruments that we have talked about before, since we had other options like thermometer, ammeter, string. So you can see thermometers are usually shaped like this for um or it can also be a form of digital thermometer, and it measures the temperature. On the right is an ammeter, and it measures electric currents, and below is a meter ruler, which measures straight line distances, like the diameter, like we talked about. It can also measure the length, width, and height of a object. It is very useful for measuring. For example, we saw this cuboid here, and these lengths, heights, and widths can be measured by a meter ruler because all the sides are straight. Then we can multiply them to find the volume. So the next question, the instrument that can be used to measure accurately the mass of a substance is, I've already put the answer here, which is A, the beam balance. So beam balance measures mass. For spring balance, it usually measures the force or the weight, especially on Earth, since weight is actually different than mass. I will cover that in a little bit. Um, Other options presents a Eureka can, which is used actually to measure volume of an irregular object. And for D, there is an option for measuring cylinder, which we have talked about before, which measures the liquid volume. And these are different units of mass, which are grams, kilograms, milligrams, and sometimes ton. So 1 kilogram equals 1,000 grams. You can think of the prefix kilo as being 1,000. So 1 kilogram equals 1,000 grams, and milli is actually you divide by 1,000. So 1 gram equals 1,000 milligrams. And there are also units of ton. 1 ton equals 1,000 kilograms. Those are different units of mass. Here was the beam balance, which was the correct answer over here. What you can do is you put the object on this pan, and there's a beam over here and a pointer at the end, which marks the 0. What you do is once you place an object on the pan, you try to balance the mass at 0 by moving these riders. These riders essentially serve as the different weight forces, different masses in order to balance any object that is placed on the pan. So you would find out the mass by finding what places these riders are placed. If it is placed at the 50, for example, like 50-gram mark, and the pointer hits 0 at 50-gram mark, then we know that that object is 50 grams. Or, for example, if the riders balance at 700 grams, for example, then we know the mass of the object is 700 grams when the pointer is at 0. The point of this beam balance is to basically balance it out. You place an object with an unknown mass and you try to balance the beam by using different um, numbers of mass on the riders. And once it balances it, we know that the mass that represents the riders equals the mass of the object. It is like balancing the scale. Eureka can, although this is measuring the volume, I included here, and you place a solid of an irregular volume. This is really useful when you place an irregular volume of solid into the liquid, and once the solid is in the liquid, certain amount of liquid overflow because this solid takes a volume of the liquid. So the liquid drops down into the separated displaced water, which can be used to measure the milliliters of the difference of the water. So that would exactly be the volume of this irregular solid. Another option was a spring balance, which is a force meter. And it measures the force or the weight of an object. So force, density, just a mass is the amount of matter in an object. We're quickly reviewing mass. And it tells us how much stuff is inside. And mass is measured in kilograms or grams and does not change based on location. So mass is not the same as weight. It's different because weight depends on gravity, but mass stays the same everywhere. For example, watermelon has more mass than an apple. Um, but for example, a rock has the same mass on Earth and the moon, but the weight changes because gravity is different. The active force on the object is different. So although the mass stays the same anywhere in the universe, the weight depends on the gravity and how much force, for example, a planet has when pulling you down by the force of gravity. So weight changes depending on location, but mass stays the same everywhere. Let's move on to a density question. So a herbal mixture has a volume of 200 cubic meters and a mass of 10,000 kilograms. Determine the density of the mixture. So density is mass over volume. This is really important. Always remember that density is mass divided by volume. The units measuring the density are either kilograms per cubic meters or grams per cubic centimeters. You cannot intertwine. So, for example, you cannot say kilograms per cubic centimeters or grams per cubic meters because these are the standard units. These are most common units that you use to measure density. But this is already given to be 200 cubic meters and 10,000 kilograms, so we can simply divide. 10,000 divided by 200 is Does anyone know the answer to the density? Yes, I think I heard 50, and that is correct. Its density is mass over volume, 10,000 over 200. 10,000 divided by 200, which equals 50. And the unit is kilograms per cubic meters, since we were given the mass of 10,000 kilograms and the volume of cubic meters. I'll make sure to be careful of the units because the units on the answer choices might be different. If so, you need to convert it by how we've talked about it before. 1 kilogram is 1,000 grams, and 1 gram is 1,000 milligrams. You can use the conversion. So the answer is A for this one. And density, to look at it more visually, is how tightly packed a matter is. It's the amount of mass in a given space. So if we have a fixed volume over here, we have a fixed volume of a square. But gas, liquid, and solid have different amount of mass in that fixed volume. For example, gas is way less dense because it has less matter in this fixed space. It is way more dispersed. Therefore, it is the least dense out of the three. Once the matter starts collecting a little bit to form a liquid, you can see that the liquid matter is way more tightly packed than the gas. So liquid is more dense than gas of the same substance. And for solid, if you imagine these smiley faces as just matter, all of these are tightly packed. And solid is the most dense out of the three. So again, density is mass divided by volume. And you can see the low density has less stuff in it, less matter in it. It's how much stuff you can put it in the fixed volume. But this has a high density. You can see more mass per volume. Therefore, it also has more weight acted on it, so it is going down this balance. The picture down here is an example of the comparison of density of water and different objects. So cork floats on water because it is less dense than water. It's less tightly packed, so that is why it floats. Wood also kind of floats because it is less dense than water. But it is more dense than cork because you can see that it sinks a little bit. The cork is completely above the water. It floats completely because it is way less dense than water. Wood is a little more dense than cork, but it is, you can see, still less dense than water since it still floats. Aluminum sinks in water. It sinks. That is why we know the aluminum is more dense than water. And you might be wondering, size does not have to do with density because although it might have a really big volume, it might have very little mass. And if you have very little mass And large volume, you would have a very small density. And even though an object might be small, it might have a lot of mass packed into it, and therefore is more dense. So the next question, the following products X, Y, Z, and W have masses of 0.05 kilograms, 50 milligrams, 500 grams, and 0.05 grams, respectively. Use this information to answer the question below. Which of the products have the same mass? So this is a unit conversion question. We have already talked about before that if the masses units are not the same, we can convert it. The best conversion here is to convert everything to grams because we already have two objects that are in grams. So we only have to convert this 0.05 kilograms into grams and 50 milligrams into grams as well. We can use the conversion. 1 kilogram equals 1,000 grams. 1 gram equals 1,000 milligrams. So X, which was 0.05 kilograms, would be 0.05 times 1,000 grams. So 1 kilogram equals 1,000 grams. If you multiply 1,000, you get 50 grams. For 50 milligrams, you multiply 50 by 0.001, or this is the same as dividing by 1,000. If you divide by 1,000, you get 0.05 grams. And the rest are all in grams. It's fine. The object Z is in 500 grams. Object W is in 0.05 grams. The question is asking which of these objects have the same mass. If we look at the same units of mass during grams, can see Y has the same mass as W. Both have 0.05. So the answer would be Y and W, which is A. Does anyone have a question so far? Is everything clear for unit conversion?
Is anybody having a question?
So everyone can convert units on their own, right? I hope so. And moving on to the next question, which are regarding chemical and physical changes. So the following processes are chemical changes, except, so we're trying to find something not a chemical change. Is it crumpling of paper, burning of wood, mixing of an acid and a base, or rusting of iron? Does anyone know the answer to this question? Yes, I think I heard A, which is correct, because crumpling of paper is not a chemical change. It is a physical change. Let's quickly review what a chemical and physical changes are. Oh, I'm sorry. We are not supposed to move on to chemical and physical changes yet because the slides are a little messed up and let's actually quickly solve another density problem because density is important. We can go back to chemical and physical changes a little later. I'm sorry about that. Let's actually solve another density problem before we move on.
Okay.
So we have the same products X, Y, Z, and W, which we have talked about here, which has, again, the same masses, 0.05 kilograms, 50 milligrams, 500 grams, and 0.05 grams. Use this information to answer the question below. If all the products have equal volumes, which of the products would have the highest density? So we are trying to find the highest density. But remember, the question stated equal volumes. So the volume is constant. We don't need to worry about volume. We just need to know the mass. So can anyone tell me how to find density again? D for density is mass over volume. So if volume stays constant, we only need to find what mass is the highest. Because higher mass leads to higher density. So highest density equals highest mass. What has the highest mass? We already found the conversion to this kilograms and milligrams before to be 50 grams and 0.05 grams. The rest are 500 grams and 0.05 grams. What is the highest here? Well, the highest mass is 500 grams. So 500 grams, which would be Z. Z has 500 grams, therefore it has the highest density. On to next question. An aluminum cube of side 2 meter has a mass 24 kilograms. Determine the density of the aluminum. What we first need to do is find the volume because we are already given mass to be 24 kilograms. We know that the aluminum is a cube. How do we find a volume of a cube? Well, we know a side is 2 meters. And since it is a cube, the length, the width, the height are all 2 meters. We multiply 2 meter times 2 meter times 2 meter because it's length times width times height for the volume of any of cube or cuboid, which equals 8 cubic meters. Density is mass over volume. So it's 24 kilograms over 8 cubic meters. 24 divided by 8 is 3. So it's 3 kilograms per cubic meters. Kilograms per cubic meter is the unit here. So the answer would be A. Is everything clear? Does anyone have any questions so far before I move on? No question? Okay. Let's look at this theory question. So this is a cumulative question. So read and record the mass of an irregular object in 1 over here, volume of water in um, this section 2, volume of water in this 3. We can see on the scale, it says over here, 40 grams. 40 grams over here. This is the mass of this irregular object. So it's 40 grams. What is the volume over here in 2? You can see that this meniscus touches 40 milliliter mark. Remember, fully milliliter equals cubic centimeters. So we can say the volume of water in part 2 is 40 cubic centimeters. What is the volume in part 3? Well, it touches this 60 milliliter mark, and we know it is 60 cubic centimeters. Second part tells us to determine the volume of the irregular object. Does anyone know how to find the volume of this irregular object? This one here. Since this is only water, this is just water. But this over here is water plus an object. To find the volume of this object, we can subtract this volume by this volume. Because water plus object minus water is just the volume of the object, right? So we subtract 60 cubic centimeter by 40 cubic centimeter, and we find the volume of the irregular object to be 20 cubic centimeters. Now let's finally calculate the density of this irregular object. Density is mass over volume. Mass is 40 grams, and we found the volume to be 20 cubic centimeters. So we divide 40 divided by 20 equals 2, and the unit is grams per cubic centimeters. So we have given in grams and given in cubic centimeters. And these are just different ways to write the units. Don't be surprised if you see G grams and then the slash for divide, centimeter cubed, or grams times centimeter. You can see the power of -3, which simply means that it is in the denominator. These are different ways to write the unit. Number 4, name the instrument that could be used to measure the mass of an irregular object. Here, like we've talked about before, we can use a beam balance and to measure the mass. Or you can also use an electronic balance, which is what we often use today. And for 5, state one precaution to be taken in performing the experiment. Well, there are many things that you can say about this, but an example might be the object should be lowered gently, not to splash the water. If you splash the water, then it'll mess up the volume calculation. You need to also be careful that you read from the base of the meniscus, like we talked about before, at the eye level, careful observation, or the measuring cylinder should be placed on a flat surface. If it's not placed at a flat surface, the reading might be a little off. Those are some examples of precaution to take when performing this experiment. Let's move on to this next theory question. It's a student seeking to determine the volume of an irregular body of mass 4 kilogram used a graduated cylinder in an experiment. This figure, figure 2, illustrates two key stages in the experiment where A indicates a setup before the irregular body was immersed, and B indicate the same setup after the irregular body was immersed. So this is basically the same as before, the before and after, with just the water and water plus object. So we know that the change in volume can see over here, you can see over here, 75 cubic centimeter after. Before it was only 50 cubic centimeters. We know to find this volume of this irregular body, simply subtracting 75 minus 50 equals 25 centimeters. Set cubic centimeters for the volume of this irregular body. Now, the mass was given to be 4 kilograms, but you need to be really careful here. Does anyone notice what you need to be careful? It's the units. So remember, density can be used as kilograms per cubic meters or grams per cubic centimeters. It cannot be intertwined together. But this is in kilograms per centimeter cubed, and this is not good. We need to convert either the kilograms into grams or centimeter into meter. What we did here is to convert um, centimeter to a meter. So what we did is since 1 meter equals 100 centimeters, this is something you guys might need to remember. Centi means by 100. So 1 meter equals 100 centimeters. So cubic centimeter, however, you need to multiply 100 centimeter times 100 centimeters times 100 centimeters. Since it's cubic centimeter, it's a little different. That is why 1 cubic meter equals 10 to the power of 6 cubic centimeters, since it is 100,000,000. This is 1 million centimeters, cubic centimeters, which equals 1 cubic meters. This can be just represented by 10 to the power of 6 because you can multiply 10 6 times to get this 1 million number. And we use that conversion for this 25 cubic centimeter, which we found here. Now it's time for conversion. Since 1 cubic meter equals 1 million cubic centimeters, we divide this conversion because we're converting from centimeter to a meter. If we divide it, we just have divided by 1 million, and we get, or we can see here, there are these both methods. If we first convert centimeter to a meter, cubic meter, then we get over here 25 times 10 to the power of negative 6. That is dividing 4 kilograms. So that is one way you can solve this question. I know that this is a little bit difficult because you need to know that the cubic meter, you need to multiply 100 centimeters 3 times. That is the key point here. What you could have done is actually way easier. You can convert kilograms into grams. This is way easier. Do you know why? Because kilogram does not have a cubic component. We can simply say 4 kilograms equals 4,000 grams. 어려운 걸 먼저 읽어봤어. So we can say that the density is 4,000 grams over 25 cubic centimeters. Both of these are the same. I've shown that both conversions can lead to the same answer of 100 grams per centimeter cubed, or if you use the meter conversion, then we get 160,000 kilograms per cubic meters. Both are good ways that you can convert these units. But the easier way definitely is converting kilograms into grams because you do not have to deal with cubic meters. Just remember, you need to match kilograms per cubic meters or match grams per cubic meters, cubic centimeters. It cannot be kilograms per cubic centimeters or grams per cubic meters. Always remember the density units. Does anyone have questions so far with the density? I think we are finished with density problems. So, does anyone have a question? No questions, then I will move on to chemical and physical changes. So the following process we've talked about before, briefly, that crumpling of paper is a physical change and not a chemical change. And if we look at the difference between the physical change and chemical change, well, physical change, there are no new substance formed. When a substance changes its shape, size, or state, for example, solid, liquid, or gas, but remains as the same substance, then we can say that the substance underwent a physical change. Examples include melting, which is a change of state, ice into water. Another change of state is boiling, water to steam. These are both physical changes. Cutting, which is a change in shape or size. We can cut wood into smaller pieces, but it is the same wood. It did not make new substances, so it is a physical change. Dissolving is another physical change. For example, sugar dissolving in water. It didn't undergo any changes to the substance. Sugar dissolved in water is still sugar in water. There's no changes in properties. Chemical changes, however, is when new substance is formed. When a substance transforms into a completely new substance with different properties, then it is a chemical change. The change is usually irreversible, meaning that you cannot undo it. For example, burning wood. If you burn wood, it turns into ash and smoke. You cannot turn ash back into wood. So we know that we found that ash is a different substance than wood. So wood undergoes chemical change when burning happened. Another example of chemical change is rusting. You see iron rusting often when it reacts with oxygen. It rusts to form iron hydroxide. Iron hydroxide is a different substance than iron. It's completely new substance is formed. That is why rusting of iron is a chemical change. Cooking is another chemical change. Since we cook a raw egg into a cooked egg, and this cooked egg is a completely new substance, and we cannot we cannot uncook an egg. This usually happens in the change in proteins. Another example includes baking, so dough baked to bread, and we cannot reverse this process. We cannot change bread back into dough. Another example is fermentation, which actually is what happens during baking as well. The little yeast actually undergoes fermentation and it produces these little oxygen, this carbon dioxide, sorry, and it puffs up the dough, making the bread. And you cannot reverse that process. That is the important takeaway here. Next question is, which of the following process is an example of a physical change? Is it fermentation of food, respiration, magnetization of iron, or lighting a match? I kind of already put the answer here, which is C. It only affects the magnetization of iron, only affects the alignment of iron, and the iron still remains iron. There are no changes when magnetization is applied. When force of magnet is applied, there are no changes to the fundamental structure of iron. There are no changes to the substance, so magnetization of iron is still itself, it's a physical change. Fermentation of food, we already talked about bacteria or yeast producing carbon dioxide, and that includes some sort of chemical compounds, chemical changes occur. Respiration also breaks down substance and form new products, so this process is also a chemical change. Lighting a match forms a new substance of ash and gases, which was not present before. So this is a chemical change. The only physical change is magnetization, where iron still remains to be iron. Let's quickly see. Um, Next question. One similarity of physical and chemical changes is that both, here I already put the answer, which is C. It produced no change in mass. This is actually from the law of conservation of mass, where it states that mass remains the same in both physical and chemical changes. So the other answer choices are incorrect because it only applies to one. For example, A are easily reversible is only for physical changes. B result in change of state in matter is only for physical change. For D, accompanied by great heat exchange only applies to some chemical changes. So C is the only right answer, and it follows from the law of conservation of mass. Mass cannot be created or destroyed and stays the same within physical and chemical changes. Let's look at this theory question regarding this chemical and physical changes. The following activities were performed in the laboratory by groups of pupils. Study the activities and answer the questions that follow. 1. Camphor was heated. So this is supposedly a camphor. And wood was burnt. 3. Iron nails were heated strongly. And 4. Sodium chloride was dissolved in water. The question asks, which of the following activities are chemical processes and B, physical processes? Well, we can see that camber was heated. It actually sublimes at room temperature. It is a change of state. So that would actually fall under physical change. What about the wood was burned? Burning of wood. We already talked about wood turning into ash and gas and also some water. So this is actually a chemical change, wood being burnt. Iron nails heated strongly, it actually forms a completely new substance of iron oxide. So iron is not the same as iron oxide, so this change is chemical change. Let's look at the last one. Sodium chloride dissolved in water. Again, this is just um, salt, sodium chloride, dissolving in water. There's no change in any substances. Salt is only dispersed in the water. So it is a physical change. To conclude, you can see 2 wood being burnt, 3 iron is heating strongly are chemical processes, and 1 and 4 camphor heated and sodium chloride dissolved in water are physical changes, physical processes. The next question asks to give 2 reasons why the activities are listed in um, chemical processes, why A are chemical processes, and why beta are physical processes. So we already talked about this before. Substance transforms into a completely new substance are chemical processes. It's usually irreversible. Why are 1 and 4 physical changes? Well, physical changes are only changes in shape or state, but remains the same substance, and the changes are reversible. That is why 1 and 4 are physical processes. Those are the reasons. Give 2 examples of physical changes that take place in your environment. This can be really anything. So, physical changes happening around you might be melting of ice or um, evaporation of water or dissolving sugar in the water. It doesn't have to be sugar, it can be any solutes or cutting wood. All of these are only changes in shape or state. They're physical changes. And we're moving on to solute and solvents. So the portion of air which acts as a solvent is, I've given you a hint, nitrogen makes up about 78% of the air. And it already tells you the answer that it's the solvent. Because moving on to solid and solvent, Because solute is the substance that gets dissolved in the solution. For example, sugar and water, sugar is the solute. For solvent, it is the substance that dissolves the solute. For example, water in terms of water and sugar. And the important point is that solvent is the one that is in the larger amount. So even if you have a gas and a gas mixture, solvent is the one with greater amount. That is why I said nitrogen is the solvent in air, because nitrogen makes up 78% of the air, is the majority. So nitrogen, since it has the larger amount, acts as the solvent. The solutes are all the other gases, like, for example, oxygen that we take in, are solutes of air. This example here shows salt and salt water, mixing of salt, the solute, the water solvent to form the salt water, which is solution. So solute plus solvent equals the solution mixture. Solute usually disappears into the solvent. Moving on to the next question. When gases are heated, they do gases melt? Do they sublime? Do they decrease in volume? Or do they decrease in intermolecular forces? Sublime basically means direct change from solid to a gas. It does not cross the process of liquid because you usually think of solid to liquid, then to gas. But sublime is solid straight to gas, does not cross the liquid phase. For example, dry ice sublimes at room temperature. But moving to the topic to this answer is D. It decreases in intermolecular forces when the gases are heated. Let's see the reason why. When the gases are heated, the gas molecules absorb heat energy and move faster. So there are particles in air and gases dispersed around. And when heat is added, um, more kinetic energy of these gas molecules increases. So what they do is that they move faster. So that is why air expands when heat is added. When heat is added to gas, the particles move faster and expansion occurs as a result. On the right, here is a really good example of heated air, heated gas. If we have a gas in this bottle here and a balloon attached, just for reference, just to see that the gas um, helps expand in volume. Once the heat is added, you can see that the gas particles move faster and faster. And once it collides with the balloon, it starts to expand. It starts to increase in volume once the heat is added. The molecules move apart, and therefore it starts to increase in volume. As a direct result, intermolecular forces weaken. Intermolecular forces are basically forces between particles. And once the particle starts to move faster, the force between these particles starts to decrease. If you think about it, it's pretty simple because the forces between particles decrease and it starts to move faster and starts to interact less. Does this make sense for everyone? I hope this doesn't make sense. So when gas are heated, it does not melt, it does not sublime, it does not decrease in volume. This is actually the opposite. When gas are heated, it increases in volume. So it's not C, so it's D, decreases in intermolecular forces. It happens when gases are heated. So the force that are keeping them together are being separated because they're moving so fast when heat is added. So the intermolecular forces weakens. And since these air molecules are colliding with every surface that they can as they are moving faster, they increase in volume. Expansion occurs. Does anyone have a question so far? Because I think we are running out of time and we need to end soon. Oh yeah, the next couple of slides include osmosis and um metalloids and maybe some standard units. Those are really short. And today we covered the major part of it. And for next time, I think we can cover the diffusion and osmosis really quickly because it's really short. And we will move on to physics next week as well. So yeah, does anyone have a final questions before we end today?
Any question? David, thank you for your time today.
Yeah.
Thank you for your time today. We are grateful for the lesson.
Yeah, I'm glad that
Your student says they don't have any question for you. So maybe if you
okay.
have a question for them, you can.
I don't
If
really
you have a
have any
question for them,
questions for them.
yeah, you can give it
Um,
out.
um, we already solved a lot of
David, what
problems
I
together.
suggest is that
Sorry, can you repeat that, please?
David, yes, I would suggest that anytime you have a lesson with them, you should at least get one assignment for them so that the following week they submit it. That will be fine. Please, you get what I said?
Oh, you want me to give them like a homework? Like a homework thing. Um,
Yes,
like
yes,
an
please.
assignment? Okay. Um,
Yes.
well,
For
I
instance,
can.
like calculation question, a chemistry question. Yeah, that should start from next week, not today. Not
So,
today.
um, I
So you prepare one question or two.
okay, yeah. Um,
Uh-huh.
if you got the slides, my assignment would be to solve the problems about density a little bit more. So I guess my
Okay.
assignment is just practice density problems on the slides that I have sent. Did you
Okay. All right.
receive the slides, the presentation?
Okay, then you can send it to Sir Prince so that you forward it to me.
We already sent it to Prince, so um, did you receive it from Prince yet? The slides?
Okay. All right. Yeah, that
Sorry,
was
did you?
last week. I've received last week's lesson.
Oh, you
I've
received
received
it
last
last
week's
week?
lesson.
Oh, last
Yes,
week's
yes.
lesson is the same. It's a continuation. So, um,
Ah, okay, all right.
yeah, it should include
Okay,
everything. Yeah.
okay. Then I've received it.
Okay, yeah, sounds good.
Okay, all
So,
right.
if the students can practice some density problems on the slides again, that would be good. Yeah.
All right, all right. I'll do that for you. I'll
Okay,
do
yeah,
that
thank
next week.
you.
We've done some, but we are not able to complete. We are not able to complete it. We've done
Okay,
some of them, but we were not able to complete. So we'll continue next week Friday, early morning before your lesson.
okay, sounds good. I will
We'll
see.
continue early morning before your lesson.
I'm sorry.
Okay, I think that's all.
Okay, yeah. Then I will see all of you next week then.
All right.
All right, bye.
Have a nice day.
Yeah, you too.
So say bye bye. All right. Bye.